All right, ladies and gentlemen, in this lesson, it's the second lesson on organic chemistry. Now, I just quickly need to make sure everybody's on the same page as me so that you don't get a surprise. In your chemistry paper, you're going to usually get 3 questions on organic chemistry. The first question will look at homologous series, naming compounds, functional groups, maybe a little bit on esters. Sometimes it goes a tiny bit into reactions, uses of them, those kind of things, okay? Drawing and naming, big focus. The second question is going to look at intermolecular forces between the different between the different molecules. And the third question is going to look at reactions. Now, when right at the beginning, I set out a plan for how many weeks it would take me to cover the syllabus, which is mainly one of the reasons I said until September, I factored in 3 separate lessons, so 3 separate weeks for question 1 of organic chemistry, question 2, and question 3. However, I suspect at this point that we may be able to pick up the pace just a little bit. So what I'm going to do today is we're going to go through 1 question on organic chemistry that would be your first type of question in an exam. And then I'm going to get started already on the idea of intermolecular forces so that many of you are in a better place if you've got prelims coming up or tests coming up or anything like that. Then next week, I'm going to be looking at electrochemistry, but I'm only going to be looking at galvanic and voltaic cells. Please, if you haven't done it at school, don't panic. I'm going to go very slowly, assuming that you didn't do very much or didn't understand very much of redox in grade 11, and we're going to build up the ideas. We will only be doing the galvanic cells in that lesson, and then what we may do after that is come back at a later stage, do another lesson on organic chemistry and another section on the electrolytic cells. So please bear with me. Each week we're only maybe going to be covering one of the questions in detail, possibly starting onto a second, but I'm not going to do all of electrochemistry in one go. There's too much content, and I'm not going to be doing all of organic chemistry in one go either. There's too much content. All right. So for today's lesson, let's share screen. Okay, let's share to the thing I wanted to do. I know that this is rather small, but I wanted to be in a position where I could see everything. Ooh. Who says, sorry, can I just quickly check? Is there anyone else who cannot hear me? If you can hear me, give me a thumbs up. Okay. All right, I'm sorry if you can't hear me. That's probably a problem with your sound. So just fiddle around with it and see if you can make it work. All right, but please always do tell me if you can't hear me, because if you can't hear me and I've got myself muted, it does happen. Okay, it's not one of those things that's beyond all reason. Okay, so with this particular diagram, I'm hoping you can see, I know it's very small, the writing, but the reason I've made the writing so small is that I ideally would like for us to be able to look at all of the compounds while answering the questions. And I actually managed to get it just the right size so that the whole page fits in the screen. Can I check, can everybody here read the writing that I've got? Give me a thumbs up if you can read the questions. Okay, so it's not so small that you can't see it. Okay, perfect. All right. So ladies and gentlemen, this is the first bit that we're going to be going through. We're going to be looking at each of these questions in detail, and I'm also going to be giving you a little bit of a chance to try and answer each question on your own. I think one of the problems with one person teaching to so many is that sometimes you get lost in the process and you don't have a chance to actually ask the questions or answer them yourself. So I just quickly, before we go any further, want to discuss what's happening in A, because I didn't cover that at all. This is called a condensed structural formula. Basically, what happens with the condensed structural formula is you start at one end of the molecule and you write down everything that you see 1 carbon at a time. So I'm going to do drawing out of A, and then afterwards I'm going to turn C into a condensed structural formula, just that you have an idea how it works. I find that this is one of the skills a lot of people don't have. And a lot of people in an exam lose marks because they look at this and they guess what it is instead of drawing it out. So if I draw this out, I start with a carbon and it's got 2 hydrogens. So I draw in 2 hydrogens. It doesn't matter where I put them, it's fine. Then I move on to a carbon with 1 hydrogen. It's only got 1 after it. Then I do a carbon with 2 hydrogens. and a carbon with 3 hydrogens. Now, if you remembered in the last lesson, I told you that every single carbon has to have 4 bonds. That means that if this carbon has 1, 2, 3, that must be a double bond. And if this carbon has 1, 2, 3, 4, it's all good. 4 is all good. 4 is all good. Okay, so that is what we mean by structure A. If we were to try and write the condensed structural formula for C, and please note you can always start from either side, so it doesn't make a difference. Here I could also have started this by writing CH3, CH2, CH, and CH2. With organic chemistry, we don't really fuss about which side we're doing it from, okay? As long as once you've drawn it out, you get the same answer, it's good. So I start on this carbon, and I'll have CH3. Then I move on to the next carbon, and I've got a C and an H. But then I need to be careful. Sometimes to show that this is a branch, it's a good idea to put it in brackets. They don't always, but I find that if I branch a methyl group off the sides, I put it in brackets so that I don't have an issue. Just for the record, I did not need to put that gap in there. I could if I wanted to. It's still condensed structural, but that's a little bit more condensed if I leave out the carbon bond. All right, so I've got my CH3, then we move on. This is a CH2. Then we've got a methyl group off it in brackets, CH3. Okay, so there was my, CH2, I left off my CH, oops, go back a step. Got to be careful when you do this. So that's the CH3, there's the CH, there's the CH3, there's the CH2, I've got to do that, but first, CH, then over here I've got my CH3, and then I'm going to be really lazy here because I could write out a CH2, CH3, but I'm about to hit the end of the page. So I'm going to make it C2H5 because I happen to know that that's just the end there. But you should technically write a CH2, CH3. All right, so I hope that that little tidbit there made a little bit of sense in terms of being able to change between a full structural formula, a condensed structural formula, and in fact we can also bring in a molecular formula. The molecular formula here, we've got 1, 2, 3, 4 carbons, so it's C4, 1, 2, 3, 4, 5, 6, 7, 8, H8, or you could have worked that out by knowing that it is an alkene and specifically butene. So you could have figured from there which one it was. All right, I'm going to quickly clear that working out. That was just a little bit of an add-in from me to make sure that everybody was on the same page before we went too far. Okay, but maybe I should leave some of this. So I'm going to leave A out, written out, because you're going to later on possibly need to go back and answer bits from it. All right, so let's get started with the real questions. Write down only the letter that represents a carboxylic acid, an ester, a compound containing a formyl group, and the compound used in the laboratory preparation of F. F is an ester. If you remember, that means it's made from an alcohol and a carboxylic acid. I'm going to quickly pause while I give you an opportunity to answer all 4 questions. So just a quick question here that somebody's done here. A is an example of a condensed structural formula. It isn't a molecular formula. Molecular formula technically lists each element only once. So it kind of groups all of the C's, groups all of the H's, and groups all of whatever other elements you've got there. It doesn't allow any repetition. Okay. All right. So I hope everybody's busy trying to figure out answers for this. Please note they did say that a letter can be used more than once. When you've got your answer, I'm going to ask you to quickly give me a thumbs up so that I know we've got there. Okay, good. Good. All right, so I'm not going to share my answer. I got that the carboxylic acid was E because of the C double bond OOH. I got that the ester was F because of the C double bond O straight onto an O. The formyl group belongs to an aldehyde. You need to memorize that. I don't know quite why, but aldehydes and their formyl groups are often forgotten. They seem to be aldehydes and ketones people seem to forget about. You don't forget about your alcohols or your carboxylic acids because you see them a lot with esters, but you tend to overlook it. So if we're looking for an aldehyde, we need a C double bond O straight onto an H. None of them have that. However, the ending of an aldehyde is ANAL, which is why the answer is D. So you had to do a little bit of stretching there with remembering what an aldehyde, well, what a formyl group was, what it belonged with, and then identifying. And the compound used in the laboratory preparation of F. So I went and split my ester down the oxygen, and I saw that it was made up of methanol. And I also saw that it was made up from ethanoic acid. And between those two, when I split it down the middle, there was no methanol here. So there was methanol, but not methanol. And therefore, I went with E because here I've got the CH3 there. That goes on to here once we split it. Okay, so that is why those are the answers. Right, I'm just clearing out a little bit more of the scribbles that I had, and then we'll move on. The more scribbles you leave on your paper, the more confusing it gets. But in an exam, you're not going to have quite as many, hopefully, as I do. All right, now we're going to practice our naming. And once again, I'm going to give you a chance to practice your own skills. So we're going to do question 2.2. I'd like you to please write down the Iupac name of compound B. But before we do that, I want to just highlight that that is a bromine. Usually you don't miss bromines. I find that the one that you do miss is a Cl. Sometimes you're so used to seeing carbons that you don't recognize the Cl. So just to point out to you that right over there, there's a bromine. Pay attention to that. And then you're asked to draw, now be very careful, to write down the Iupac name. Something I never mentioned in the last lesson is that Iupac names or Iupac nomenclature is, and I always get confused on this as well, the International Union of, I think it's Physical and Applied Chemists or something. I always get confused with the P. Pretty sure at this point I'm going with physical, but there may be a word I missed there. But it's basically a body that meets, that decides how we're all going to be naming our compounds, that we do the same naming. I always use the example of some people call a brinjal an aubergine or an eggplant, which isn't really a big issue because you can eat it regardless of what it's called and nobody's going to charge more for it depending on what it's called. In chemistry, if you're the first person to discover a new compound, and that compound happens to be the cure, I'm picking on a very topical thing, but the cure for coronavirus, and you get it and somebody else across the world gets it and you both give it different names, you're going to have legal fights for years. So to make sure that when you publish what you've got and someone else publishes what they've got, you're both talking the same language. We all use Iupac naming so there isn't this confusion. Now, when it asks for the Iupac name here, it wants a positional isomer of compound A. So basically, it wants us to look at compound A, but change the position of the functional group before we write down the name. All right, I'm going to pause sharing and give you a chance to quickly do that. I have a sneaky suspicion some of you have already finished while I've been talking. But that's okay, that's your problem. Go for it. All right, if you've got both of those, you can give me a thumbs up so that I know that you're done. Okay, well done. Some of you are there very fast. Can't decide if I'm expecting you to do this too quickly if I say that now's time up. I think you maybe got a little bit more time. Okay, guys, you got to help me. What's the theme today? Is it sports? I'm going to be guessing every week. Okay, yay. And was it under the sea or aquatics last time? Okay, awesome. Well done. Good effort. I'd say you should let me know as well, but I'm probably the person who'll forget every single time and make a half-hearted attempt. So I'm not going to bother. All right, ladies and gentlemen, I think that's enough time. So I'm going to quickly share my answer with you. If you look at B, you'll see there's the bromine and there's the methyl group. We've got to start numbering from the end with the bromine on it. So we've got a bromine on carbon 1 and a methyl on carbon 2, 3 carbons in total. So it's 1 bromo, 2 methyl, propane, because there's no double bonds or triple bonds. Because we weren't just asked for compound A. Compound A would be 1 butene or but1ene. Compound, the positional isomer has to move the double bond. Now, if we move the double bond right to the end, we actually just start numbering 1 from this end. So it's still 1 butene. So the only place that you could move it to is over there. I'm going to quickly undo it so I haven't changed what the molecule is. But that's the only place that you could move it to. And because of that, our answer is but2ene. All right, I saw there were 2 questions there. Oh, okay, sorry, the theme. If you open up so that you can see all of the people that are talking and not just me, we've got a group of students who every single week dress up. Well, not every single week, 2 lessons now. They've been dressing up to a theme. So I'm going to quickly stop sharing. No, I won't, because if I stop sharing, you won't be able to see. When I stop sharing, you'll have an opportunity to look at the theme. Until then, I think you guys are all stuck looking at me and you don't get to look at each other. I get to look at you though. All right, so that sounded very creepy. Let's carry on. Question 2.3 says, draw the structural formula of compound D. I haven't yet done that, so I'm going to quickly pause and ask you to please do that. Oh, sorry, good point. Sorry, somebody's just shared something and it's vitally important. I come from an old school where we were allowed in the very, very olden days to put a dash between methyl and propane. You are officially not allowed to do it, so there should not be a dash there. Every now and again, I find I get caught out by it. I try not to, but it's what I learned when I was in school, and sometimes these things come back to bite you if you get taught incorrectly. All right, so I'm just going to quickly pause there. At a university level, nobody's really fussy about that dash, but they get fussy about it in matric and it will lose your mark each time, so don't. Okay. So all of you should be drawing out methanol at this point. Okay, if you're done with it, give me a thumbs up. Okay, good, good. Good, okay. All right, so I'm going to share it relatively quickly because I do want us to get through onto the next bit. Over there, we've got our methanol. Please note that's a functional group. It's only got 1 carbon, so just stick an H off the end. Ideally, you should just have that drawn exactly that way. I would also recommend, and this is very important, in your matric exam, draw your pictures in pencil. If you make a mistake, it's much easier to erase and write them again. I can promise you none of your teachers will have this desire, I hope, to go and erase your answers. They also shouldn't have an opportunity to go and change your answers. But I find that drawing them in pencil for diagrams makes it a lot easier. If you draw them in pen, it gets rather messy. Okay, jumping back to what we did at the end of your last lesson, it says write down a balanced equation using structural formulae for the formation of compound F. So you need to tell me which carboxylic acid will draw for me, which carboxylic acid, which alcohol were used. I would recommend that you put in the catalyst that you use and you write out a full equation using structural formulae for the formation of compound F. I'm also going to remind you here, because I know it's where you're going to lose your marks, please remember to draw out water properly. All right, so So I'm going to pause. I'm going to draw it all out. I'm hopefully going to squeeze it in, and then we're going to compare. All right, go for it. Okay, I'm going to quickly ask who's already done. We got the answers already. Managed to draw it out. Good. Unfortunately, when I show you my answers, you're going to find that I don't have enough room on my whiteboard. So instead of going starting materials, arrow, products, I go starting materials, arrow, products. You don't do that. You've got enough space to go left to right across the screen. I've got a whole picture in the middle of my screen that's unfortunately stopping me. All right, was there a question? Not certain if someone's got a question. Okay, cool. All right. Okay. I'm going to assume that everybody's okay with that, and I'm going to resume my share here. Okay. Still trying to figure out why it's decided I'm not talking. I'm not muted, am I? No, not me. Okay. All right, so I'm going to quickly resume my share. If I resume my share, here's my working out over here. So over there, I've got my ethanoic acid and my methanol. Please remember to join them functional groups together. When I draw them both with the functional groups together and I take out the water and they join directly onto each other, that produces the ethanoic acid and the methanol that you, well, sorry, the product that you see over there, which I haven't actually named, as well as the water. I am not quite certain how they do this for 2 marks, because my feeling is usually it's 1 mark for each of these and 1 mark for the water. However, I have a sneaky suspicion that since they already asked you about ethanoic acid over there, they probably felt they didn't need to give you a mark for drawing the ethanoic acid. And because of that, they decided that they weren't going to give you the mark for drawing the ethanoic acid. All right, so that's pretty important for that bit. Over here, it also then, sorry, just one other thing that I wanted to discuss with you. It didn't ask you to name the ester, but I'd like to just quickly ask, can everybody please tell me what, or write down what the name of the ester F would be? Just quickly, I'm not going to pause. I just want to quickly give you a chance to write down what F would be. Okay. I'm still sharing. Good. I get that the name of F is fantastic. Methyl ethanoate. So it's alcohol aryl carboxylic acid OH. Don't ever write that in an exam. It's not a thing, but it's methyl ethanoate. So it's just a handy way to remember to do it. Last question asks you to write down the Iupac name of the unbranched isomer of compound C. So if we're dealing with isomers which have different chain lengths, okay, just quickly, would it be a problem if you started with the alcohol first? Okay, so Dumasile, if you're asking about drawing these two, you can draw them in either order. There's no rule as to what you have to draw first. I must be honest, I think the reason I drew it this way around is it was easier for me to see from here which way around they went. But the people who are marking your papers are used to the fact that they can draw them either way. Okay. I know in the Western Cape in particular, our examiners actually have to pass a competency test, and it's a hard test. So they make certain that we're able to read things backwards, etc. And my impression for the rest of the country is that they also have similarly qualified examiners who are very good at organic chemistry and will pick up all of those things. But I'd recommend to make sure that it looks like the memo. It's probably not a bad idea to do it in the order that it's drawn here, if it's possible. Okay, if it isn't possible and they give you the name, then you can draw it in either order and it isn't a problem. All right, but I'm telling you, if they've drawn this out for the question paper, they've probably got it on stock file to quickly stick into the memo. All right, we had to write down the Iupac name of the unbranched isomer of compound C. Another word for unbranched is linear. So we are dealing with 2 isomers of C. Here we've got the branched because it's got 2 methyl groups over there. So if we're doing the unbranched isomer, it's still going to be an alkane, and it's going to have 1, 2, 3, 4, 5, 6, 7, 8 carbons in a row. Hence, the Iupac name for the unbranched isomer of compound C is, anybody? Anybody? Okay, nobody's offering. Yay, somebody's offering. Good, it's octane. Okay, so it's octane. Technically, we could do different isomers that are differently branched, but since they specifically said unbranched, it has to be octane. And we would regard C and octane as being chain isomers. Now, I want to ask just a couple more questions while we're on this section so that we don't have a situation where we move on and then you come across a lot of things you can't do in tests. You're going to come across a few, but I don't want you to come across lots. Now, my first question here is compound B a primary, secondary, or tertiary haloalkane? Okay, you're welcome to unmute yourself and shout or to chat, depending on how you feel. Anyone? Compound B, primary, secondary, or tertiary? Okay, and we've got an offer. It is primary. In fact, we've got 2 offers that were right and then 1 that was wrong. The bromine is attached to this carbon, and this carbon has got 1 carbon neighbor, which makes it primary. If we had instead stuck the bromine in this position, then it would be attached to 3 carbons, which would make it tertiary. So primary, secondary, and tertiary refer to the number of other carbons, the number of neighboring carbons on the carbon that the functional group is attached to. We usually deal with primary, secondary, and tertiary when we're dealing with haloalkanes or when we're dealing with alcohols. The other section that I just glossed over slightly in the last lesson was the idea of functional isomers. Okay, so with the idea of functional isomers, we're going to be talking about how we can make a functional isomer of 2 different substances. Okay, maybe, yes, 2. Okay, so if I were to start with this E here is a carboxylic acid. Carboxylic acids can only be converted to esters if we need to make a functional isomer. And if we've got to turn a carboxylic acid into an ester, the ester can only contain 2 carbons. Esters, because of the way that they're set up, must have a carbon on either side of the functional group. So the only functional isomer that we could draw of compound of ethanoic acid, compound E, is if we drew something that looked like this and had 2 carbons in total, 1 here, 1 here. Now, what I mean by functional isomers is this will have a formula of C2, count them, H4, O2. This will have a molecular formula of C2, H1, 2, 3, 4, O2. So you can see that they're isomers because they have the same molecular formula, and you can see that they are effectively functional isomers because they have different functional groups. I am now going to challenge all of you that I would like you to please draw the functional isomer of compound F. Bearing in mind that I've just told you that carboxylic acids and esters will be functional isomers of each other. A hint here is this is the ester. Can everybody please try and draw for me the functional isomer of compound F? I know I'm asking you things that are beyond what the test asked, but it's a good opportunity. If we give you the pictures here, we may as well use them. Okay, so quickly draw for me what your functional isomer would be. Structural formula, but sometimes we'll ask you for the Iupac name, but I'm starting on structural formulas just at this point. Okay, can I ask if you've already got that done? Quickly give me a thumbs up. Okay, well done. Great. All right, so I'm not going to take too long. I still want to get onto intermolecular forces. So let's resume my sharing. The first thing that I knew was that since the original functional group was, or the original, homologous series was an ester and it contained three carbons, I must have a carboxylic acid with 3 carbons, which means that I get propanoic acid. Okay, also a little bit more testing on your naming. Can I ask everyone to just quickly, it shouldn't take you very long at all, jot down the name of this ester that was the functional isomer of ethanoic acid. Quickly write it down. It's not going to take long, just practicing naming. Okay, I'm going to presume you've all already got it. This is methyl methanoate. Okay, and something that you should be aware of is that sometimes if we go from an ester to a carboxylic acid, there's only one possible isomer. But if, for example, we went from propanoic acid to esters, we've got an option that 2 carbons came from the carboxylic acid and 1 came from the alcohol, or we could have had 2 from the alcohol and 1 from the carboxylic acid. So from propanoic acid, if I were to ask for functional isomers, you could either have methyl ethanoate or ethyl methanoate. Both ways, the meth-eth can go either way in order for it to work. All right, ladies and gentlemen, I'm going to stop sharing at this point. If there's anything that you need from the screen, quickly take a picture of it. And then just one last reminder, because I promise you this is where you're going to lose your marks. I don't know why, it's not difficult, but most people forget to draw out water like that. They write H2O and they forget that this is a molecular formula and this is a structural formula and they're different. Okay, one last question. Yes, you can say that ketones and aldehydes are also isomers, and in fact, while we're here, we may as well do that. So the alcohol, the carboxylic acid and the ester are functional isomers, and a ketone and an aldehyde will also work. So while we're at it, I'm going to quickly clear it, and I'm going to ask you, this is very important. So we've just said that an aldehyde will have a ketone that is a functional isomer. Is that the case with methanol? Does methanol have a ketone that is a functional isomer? And who can tell me if it doesn't, which it doesn't, why it doesn't? Any answers? So please remember with these that there's sometimes exceptions, like our carboxylic acids have to have at least 2 carbons. I can't deal with methanoic acid and make an ester from that because I need 2 carbons for that. I guess I've already answered my question, and it doesn't look like anyone else is going to. Any volunteers as to why it was methanol? Okay, we got 1. Okay, because it's only got 1 carbon and it's technically going to need 3. So I'm going to tell you right now that if I have, let's say, for example, butanol, aldehydes do not need you to ever number the position of the aldehyde group because it's a terminal group. It's a little bit like a carboxylic acid. We can say ethanoic acid. We never need to say one ethanoic acid or two, or well, one butanoic acid, because your C double bond OOH is what we call a terminal group. It's always going to be on the end. So if we're dealing here with an aldehyde, because it's a C double bond O straight onto an H, hydrogen can only be at the end wherever this is. So it's what we call a terminal group. Can I ask all of you to please draw for me right now the functional isomer of butanol? I should probably say any functional isomer of butanol, but I'm going to be cheeky and tell you that there's only one. Okay, quickly draw it. Oh, sorry, I didn't finish that. Let me just quickly get no, yeah, I don't need to draw this. This isn't butanol. There we go. So I'd like the functional isomer of butanol. There we go. Please draw all of your hydrogens in every single time. Okay, if you've got an answer, give me a thumbs up. Okay, good, well done. All right, I'm going to share with you now. So butanol would be the aldehyde, and the ketone that we get from it is 2-butanone. Please note it wouldn't ever be 3-butanone. I can imagine some people naming it, but you'd number 1, 2, 3, 4. You wouldn't name number 1, 2, 3, 4, because you must always number from both ends. Some of us don't need to do it every single time. But if you look at these two, you'll see that you always go with the lowest numbering system, which is why you'd make it a 2, not a 3. You always want to have it on the lowest possible number that it could. All right. I don't know if anyone needs to take a picture of that. I think most of you should be good with it. So I'm going to quickly clear, and then I'm going to stop sharing. All right. Ladies and gentlemen, can I quickly ask all of the people who are dressed up, just so that the people who aren't can get an idea of what I'm talking about? Now I think everybody can see you. There you go. You can see that there's kind of a sporting theme. The cricket bat was actually what gave it away. The rest of you guys made it very confusing. All right. Okay, and the gum guard and the hockey, I did get that. All right. So ladies and gentlemen, can I just quickly check who found that that particular exercise cleared up some of the issues that you may have had with naming or with any of the different other aspects? Anyone? Okay, cool. Looks like most of you know what we're doing, which is actually a really, really good sign, because I think that indicates that your organic chemistry is not very weak. What I'd like to do, if everybody is okay with it, we do actually have a choice. We could either do another exam question, or we could move on to intermolecular forces in organic chemistry. I think we've got just over 20 minutes left, which should give us enough time to do a very superficial version of intermolecular forces. But the good news is a superficial version of intermolecular forces is normally sufficient. So is everybody good with me doing intermolecular forces? Takes us a little bit further into this. It does mean that at the end of this, you will be able to answer both the question 2 and 3 from most of your chemistry papers. All right, so let's get started. I'm going to work on my whiteboard now, and we're going to get the ideas. Now, please, if you are at an IEB school, you focus on the same idea behind intermolecular forces, the same types of intermolecular forces, but what you do that's different is you get examined on what the CAPS students, the NSC students, only do in grade 11. So in grade 11, we looked at intermolecular forces dealing with anything. When we hit grade 12, we suddenly only look at intermolecular forces in detail when it comes to organic chemistry. They may drag them up every now and again with other sections, but they usually don't. They tend to leave them alone and let that be the end of it. So when we are dealing with the idea of intermolecular forces, we are effectively looking at the types of forces between the molecules. Okay, if you look at the word intermolecular, between molecular, between molecules. And these forces between molecules are very important. If you remember back to grade 10 and possibly quite a way before then, you learned that the difference between solids, liquids, and gases were how strong the forces were between the particles, and that's what was responsible for them being solids, liquids, or gases. We also learned that those intermolecular forces were responsible for the boiling points and the melting points. Usually we only care about boiling points if we're talking about a liquid, because liquids will boil next. And we usually only care about melting points when we're talking about a solid. So that's just a little important thing. Don't always throw melting point and boiling point in together. Think about whether you're likely to boil it next or melt it next. Along with this, we're going to be introducing a couple of new ideas. They should have been introduced in grade 11, but we're going to quickly look at them as well, which are the idea of vapor pressure. And vapor pressure is the pressure of a gas in equilibrium with its liquid. And effectively, vapor pressure and boiling point are linked. If something has got a high boiling point, you need to put in lots of energy in order to turn it into a gas. And if you've got to put in lots of energy at any temperature, you've got to raise or get to a higher temperature to get it to boil, you're going to produce relatively less gas. Think about it. You've got to put in lots of energy. It's not going to boil. It's not going to make a gas. And therefore, the pressure of that not going to make a gas is going to be low. Because if you've got a lot of gas, you've got a lot of gas pressure. Please remember that vapor is another word for gas. So we look at that. The last thing that we can look at, but we usually don't, is the idea of viscosity. Viscosity has to do with the pourability of a liquid. So if something has a very high viscosity, it's gloopy, okay? So the particles are very attracted to each other, and therefore when you pour it, it gloops like a gel or like honey or like sometimes even oil. If something has a low viscosity, it's going to pour really easily. So generally water is regarded as having a low viscosity. Okay, so high viscosity means high intermolecular forces. So I'm just quickly going to go and do a quick kind of brief thing. Just give me a second. If we have strong intermolecular forces, the substance will have a high boiling point, a high melting point, a low vapor pressure because it's not going to boil and produce a large amount of gas. It'll produce very little gas if it does start boiling, and therefore there'll be less pressure from the gases, and it will also have a high viscosity. But we're going to come back and explore those ideas hopefully in the next session where we hit the questions on this section. All right. Now, within the types of intermolecular forces or the factors that affect intermolecular forces, I'm going to go with factors first. There are three factors that you can use or that affect the intermolecular forces. Sorry, I've got a 9-year-old who's baking and he keeps running taps and making noise. So the three factors that affect the intermolecular forces are, first of all, the type of intermolecular force. This refers to whether we are dealing with, and please note, different schools use different names, but they're all the same thing. The weakest type of intermolecular force are called our London forces, but some of the schools call them induced dipole forces. Got to put in all of the words here. You leave one off and they mark it as wrong. So it's induced dipole forces, or they are known as dispersion forces. Please, you do not need to worry about using all of them, but all of them are correct. Okay, the second type of intermolecular force, yeah, all of those were one, are our dipole forces. And I can promise you firsthand, I got to mark this paper last year, that if you just write, well, this question, if you just write dipole forces, it's wrong. You effectively make it really easy for us to mark if you leave off a dipole, because if you write dipole forces, we don't have to read the rest of what you've written because I can't give you a mark for it anyway. Okay, so it's got to be dipole forces. And then lastly, we have our hydrogen bonds. Okay. So the factors that affect the intermolecular forces are the type of intermolecular force, which one of the three it is. I'm going to explain to you which molecules fit into each of these. It actually makes it really easy to know because you then just identify the homologous series and go snap, it's that one. Okay. The second thing that affects the type of intermolecular force is the length of the carbon chain. Okay, so that effectively says if we're comparing methane, ethane, propane, the bigger the mass is, the stronger the intermolecular force. So we either say the length of the carbon chain, or we can describe it as being the molecular mass. Okay, so this comes down to the fact that if you have a longer chain, you'd have a higher mass, you'd have more protons and more electrons interacting, stronger intermolecular forces. So longer chain always means stronger intermolecular forces. And then the last factor here is, and they also give many different options for this, the amount of branching. Oh, what am I spelling there? The amount of branching, which has to do with whether you've got a linear chain or whether you make an isomer and have methyl groups and ethyl groups branching off it. Instead of saying the amount of branching, sometimes they appreciate you talking, or they allow you to talk about how linear they are, how spherical they are, or we could link it directly to the surface area. But I usually find that I talk firstly, that's area, about the amount of branching, and then I personally link the amount of branching to the surface area. All right, can I just quickly check who is still with me? Does this all make sense in terms of what you've learned before when you were at school? Okay, good. Now I'm going to try and just kind of bring all of this together in one go. And I'm first of all, and I know it's a very bad analogy, but I find that my bad analogies work very well in my head, and hopefully they make good sense in your head. So I'm going to be dealing with these two factors here, which are the length of carbon chain and the amount of branch. And I'm going to be talking about the idea of Velcro. Now, in case any of you don't know what Velcro is, stuff is Velcro. It's stuff that when you get two pieces, one's got little hooks on it and one's got kind of fluffy bit, and you stick them together and then you pull them apart. Now, I regard how sticky the Velcro is when it sticks together to be linked to the strength of my intermolecular forces. That's how much they want to stick together. So how much force I have to apply to separate them indicates the strength of those forces. Now, I want you to just imagine in your head. Before I go any further, let's just quickly check if this analogy is actually applicable. Does everybody here know what Velcro is? Is there anyone who doesn't know Velcro? Just making sure that this is an example that all of you have real life experience with. Velcro, thumbs up if you know Velcro. Gosh, none of you know Velcro. Okay. We got some of you I think have fallen asleep. Okay, so now we're going to talk about the length of the chain. If I've got two short pieces of Velcro and I stick them together, little force to pull them apart because they've got weak intermolecular forces. If I take an exceptionally long piece of Velcro and push it together, because we've got a longer length, there'll be more forces and therefore they require a greater amount of energy to pull them apart. So I always say the longer the chain, the stronger the forces, but I imagine it in terms of how long a piece of Velcro is as to how much force I have to apply to separate it. The second bit deals with the amount of branching. Now, when we branch our chains, we actually make the entire structure more spherical. So I know we always have these pictures where we imagine things like we imagine these long chains of carbon, and then when we picture off the side that maybe instead of having 5 carbons in a row, we have one branched off it. We imagine it like this one's nice and long and skinny, and this one's nice and long and skinny with a tiny bit sticking out. That's nonsense. This turns into a giant thing. So it effectively takes it from being nice and long and skinny, these all look like caterpillars, by the way, to being like squashed and very spherical. And the more spherical it is, the smaller the surface area is. So if I look at my example of Velcro, I imagine branching in Velcro is like taking a long thing of Velcro and scrunching it up into a ball. Now, if I scrunch it up into a ball and then I try and stick it to another piece of Velcro, it's going to have fewer points of attachment. Okay, so if I've scrunched it all up and I now try sticking it against the other piece of Velcro, only certain pieces of the surface area can come into contact, which means that there will be fewer interactions and it will require less energy to pull it off because it's got weaker forces. So my rule here is that the more linear it is, the less spherical, the less branched, okay, the more surface area it has, and the more surface area it has, the stronger the intermolecular forces. Okay, so that's the idea I want you to have in your head when you're looking at these things, is to just always imagine that that's how everything links together. All right, can I quickly check? Has everybody got this nicely? And can I clear it? Is everybody good with that? Quickly say yes. Thumbs up. Okay, cool. A few of you said thumbs up. That's good enough. Now what I want to do is I want to touch on the types of intermolecular forces and what substances we find there. It actually makes it a really easy way to do it. So I'm not going to go into great detail as to where any of these intermolecular forces come from. That unfortunately is a grade 11 job, and if we're going to go into that, it's going to take a really long time. So instead, I'm just going to look at the fact that we get London forces. We get dipole-dipole forces. Both dipoles are important for your mark. And lastly, we get our hydrogen bonds. Now, you need to know from all of the homologous series that we discussed which one goes where. So the most important thing is that all of your hydrocarbons have got London forces. Remember, hydrocarbons exist with only hydrogen and carbon in their molecule. So that means that our alkanes, alkenes, and our alkynes fit under the category of London forces. As a rule, London forces exist between molecules that are completely non-polar. So they are non-polar molecules, and therefore they get London forces. It is also possible for you to get some symmetrical haloalkanes that fit into this category. And those would be things where, I don't know, if we've got C, Cl, 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 like carbon tetrachloride, what you'll find is because it's got a perfect, even though these are polarized bonds, the symmetry makes it completely non-polar, and therefore it will have our London forces. Okay, let's wait a second. I'm trying to see what the question was in the chat. All right, no, Gabby, they're not going to test you at matric level on any of the other types of intermolecular forces. These are the ones. You're safe if you know these. Okay, I doubt they'll ever bring in anything else. Please note that doesn't apply if you are doing IEB. IEB, they bring back everything from grade 11. NSC, you don't have to worry. Now, with these being between non-polar molecules and London forces, these are the weakest type of intermolecular forces. I find that the easiest way to split our types is to do the extremes. London forces, weakest. Hydrogen bonds, strongest. And then we deal with anything that I haven't mentioned under dipole-dipole. So with our hydrogen bonds are the strongest type of intermolecular force, okay? And with these, they are between, and they get very specific, they exist only if you have hydrogen and a small electronegative, I'm going to move my picture, electronegative atom. So they only exist when you've got hydrogen and a small electronegative atom, and those small electronegative atoms are nitrogen, oxygen, and fluorine. Only if there's hydrogen, nitrogen, oxygen, or fluorine will you get hydrogen bonds. Now, when you were in grade 11, you'd have learned about ammonia being an example, and water being an example, and hydrogen fluoride being an example. None of those are organic. So the only thing that we really focus on are our alcohols and our carboxylic acids. Okay, you've got it. This, what I'm writing down here, you kind of got to memorize this that you don't mess up. Now, they're often going to give you a question where they pick on an alcohol and a carboxylic acid of similar molecular mass, and they ask you which of them will have stronger intermolecular forces. The rule is carboxylic acids have 2 sites for hydrogen bonding because they've got 2 oxygens. So because they have 2 sites for hydrogen bonding, they usually have stronger intermolecular forces than alcohols of a similar molecular mass. Okay, obviously, if we were to deal with different molecular masses, it is possible that we can also get an alcohol that has a higher, a stronger intermolecular force than a carboxylic acid, but provided we're comparing apples with apples, similar masses, and we're just, the thing that we're changing, okay, is whether it's a hydroxyl group or a carboxyl group. Remember, alcohols have hydroxyl, carboxylic acids have carboxyl. If that's the thing that we're testing, then you'll find that carboxyl beats hydroxyl every time. So alcohols only have 1 site for hydrogen bonding. Okay, and then lastly, down the dipole-dipole forces, you can include in here your ketones, your aldehydes. The oxygens tend to be usually very electronegative, so they become slightly negative, and therefore they make the whole thing polar. Your alcohols, remember, are an extreme version, so they fall under hydrogen. Your haloalkanes, provided they're not symmetrical. Can't see if I've left anything out. Your esters. All right, so what makes this easier is if you're comparing 2 molecules, and you can see they've got a different homologous series, they'll have a different functional group, and they may have different kinds of intermolecular forces. They normally make sure that we compare between the different groups, okay? So they're not likely to make you compare a ketone and an aldehyde. That gets tricky. But they're very commonly going to make you compare hydrocarbons with anything in the dipole-dipole group, or hydrocarbons with anything in the hydrogen bonding groups. They usually compare across 2 groups. If they're comparing within the same group, that's when they're usually looking at the difference between how branched they are or how long the carbon chain is. Okay, so the strongest type of intermolecular force, depending on the type, is your carboxylic acids, because they're the strongest hydrogen bonds because they've got 2 sites. Weaker than that is our alcohols because they've only got 1 site. After that is anything that's dipole-dipole. And then after that still is London forces. Now, a relatively recent development that they have started to hint at least in the Western Cape with how we get tested, I can't speak for all the other provinces, so that's why I'm clarifying, is we also recognize that London forces actually are found in every single organic molecule. So every molecule will have a small amount of London forces. London forces exist purely because they've got electrons, and their electrons are spinning around the nucleus. And at some point, you'll have more on one side of the molecule than on the other, okay? More side of the atom, whatever. So with our London forces, they've started something where we advise our students that whenever you answer, you'd say it's got London forces, or it's got dipole-dipole forces and London forces, or you say it has hydrogen bonds and London forces. We haven't yet reached the point where we penalize you if you leave off and London forces, but it may be one of those things that your teachers have already advised you to start putting in. My recommendation, always write which one of these it is first and add the and London forces on as kind of additional information. All right, I'm just going to quickly pause sharing there. I wanted to ask just quickly, has anyone else's teachers done the and London forces with him? Quickly, if you have. If your teachers have done and London forces, okay, cool. Very funny. Some of my students aren't yet putting up their hands. All right. So you need to make sure that you're aware of that. All right, ladies and gentlemen, we are effectively at the end of today's time. So just quickly need to check. There was one question. Okay, that was a nah. All right, so we're at the end of today's time. In your lesson next week, I'm going to be looking at electrochemistry. All right, so galvanic and voltaic.